This course is about the basic foundations of computer science, and there's nothing more foundational than numbers. In order to do anything mathematical in computer science, our first order of business is to understand how computers handle numbers, and that's what this video is about. By number, for now we're only going to mean non-negative integers. An integer is simply a whole number, something that isn't a fraction or a decimal. So for the time being, when we say number, we mean 0, 1, 2, 3, and so on, and we will leave negative numbers and fractions or decimals out of the picture for now. Let's first think about how we as human beings think about numbers. Look at the number 275. When you were a kid, you learned that this number has 3 digits, the 2, the 7, and the 5, and those digits appear in different places. The 5 is in the ones place, the 7 is in the tens place, and the 2 is in the hundreds place. Let's think about those places. Each place in a number is a power of 10. 1 is 10 to the 0, 10 is 10 to the 1, and 100 is 10 to the 2. The digits are there in those places to tell you how many copies of that power of 10 to use. So 275 uses 2 hundreds, 7 tens, and 5 ones. We could write this by pulling apart the different places and writing 275 equals 200 plus 70 plus 5, which is 2 times 10 to the second plus 7 times 10 to the first plus 5 times 10 to the 0. So we can write 275 as a sum of copies of powers of 10, and the digits we use tell us how many copies of each power of 10 to include. To take another example, look at 17,025. This has digits not only in the ones, tens, and hundreds places, but also the thousands and 10,000s places. This can be written also as a sum of copies of powers of 10. 17,025 is 1 times 10,000, plus 7 times 1,000, plus 0 times 100, plus 2 times 10, plus 5 times 1, or 1 times 10 to the fourth, plus 7 times 10 to the third, plus 0 times 10 to the second, plus 2 times 10 to the first, plus 5 times 10 to the 0. What those very simple examples illustrate is the fact that every non-negative integer can be written as a sum of copies of powers of 10, and the number of copies ranges from 0 to 9, which are the digits of the number. This format for writing numbers is called the base 10 or decimal representation of the number. The word decimal here doesn't mean fractions like 3.14. It uses the prefix deci, which means 10. So the decimal representation of a number is our usual way of writing things, where the digits refer to copies of powers of 10 in different places. Why do we use powers of 10? It's simply because we're human beings and we have 10 fingers, and long ago this is how we learned to count. If we had evolved to have 8 fingers or 16 fingers, then things would have turned out differently. Humans, like you and I, store and process numbers in decimal form. All the arithmetic you learned when you were a kid, for example, uses base 10 representation. Computers, on the other hand, are not human and do not have 10 fingers. Our use of base 10 representation makes no sense to a computer, despite the fact that computers seem to have no trouble working with numbers. But in fact, below the surface, in order to do any math on a computer, and the only thing the computer actually does is math, we have to learn how to translate from our world of numbers to theirs. How do we do that? So you have an understanding that computers are electronic devices, so they only understand 2 things, on and off. Computers process electrical pulses that have only those 2 states. We usually represent those 2 states with either a 1 for on or a 0 for off. So whereas we humans have literally 10 digits on our hands and therefore 10 digits used for numbers, computers only have 2 digits. Since there are only 2, we refer to this as binary rather than decimal, and the term binary digit is usually shortened to just bit. Everything you see a computer do, including the playback of this video, your word processor, that video game you like to play, it's all just an extremely long string of bits telling the hardware what to do. Any information processed by a computer is in binary, including numbers. So how is this done when you only have 2 digits? Just like we can write every number as a sum of copies of powers of 10, it turns out we can write any number as a sum of copies of powers of 2. When we do this, we create what's called the base 2 or binary representation of that number. Because we're going to be using powers of 2, here they are from 2 to the 0, which is 1, all the way up through 2 to the 11th, which is 2048. Hardcore computer people might recognize 2 to the 10th or 1024 because that's the number of bytes in a kilobyte. I highly recommend you learn these powers of 2 so that they are as familiar to you as the powers of 10. Look, for example, at 275 again. Although it's not necessarily easy to see, we can write this number as a sum of powers of 2 like this. 275 is 256 plus 16 plus 2 plus 1. All those are powers of 2, and there were several that we skipped. In this representation, we used 1 2 to the 8th, 0 2 to the 7ths, 0 2 to the 6ths, 0 2 to the 5ths, 1 2 to the 4th, 0 2 to the 3rd, 0 2 to the 2nds, and 1 2 to the 1st, and 1 2 to the 0. The binary representation of the number 275 is the string of digits you see in the second row, 1 0 0 0, 1 0 0 1 1. Notice importantly that unlike decimal representation, where we use the digits 0 through 9, in binary the only digits we ever use are 0 and 1. We'd never see a 2 or a 5 or a 7 show up in binary because this would simply mean we could just use a higher power of 2. It's just like how you don't see a 13 show up as one of the quote-unquote digits in a decimal representation. Here's another example of changing a decimal number to binary. 1902. That number can be written as this sum of powers of 2. 1024 plus 512 plus 256 plus 64 plus 32 plus 8 plus 4 plus 2. So we have a 2 to the 10th, a 2 to the 9th, a 2 to the 8th, then a 2 to the 6th, 2 to the 5th, 2 to the 3rd, 2 to the 2nd, and 2 to the 1st, and no other powers of 2. That means the binary representation is 111, 0, 11, 0, 111, 0. It's not totally clear right now how we can easily split up a number into a sum of powers of 2 like this, other than through guess and check. But don't worry, in a later video we're going to present a speedy algorithm for doing this, which will make it easy to convert representations from base 10 to base 2. But notice that converting the representation in the other direction, from binary to decimal, is on the other hand pretty easy. For example, look at the binary integer 10101100. This representation is saying this number is 2 to the 2nd plus 2 to the 3rd plus 2 to the 5th plus 2 to the 7th. And a calculator will tell you that that is the decimal number 172. Just use the bits to tell you which powers of 2 to include, find those powers of 2, and then sum them up. So in this video, you've learned what our primary school concept of base 10 representation means, what a binary digit or bit is, what base 2 or binary representation means, a basic first idea of how to convert an integer from decimal to binary representation, although we're going to improve on this in a later video, and how to convert from binary to decimal. That's a big step towards being able to understand how computers and computer programs really work. Congratulations, and see you in the next video.